presentation, I left one question, that is for wonderful equation, where we use mu as 1,000 and t equals to 3,000 and that, and to try to solve it using ODE equal 5. Otherwise, the memory will be all occupied. The memory, there will be overflow in the memory. So, this kind of equations are called steep differential equations. So for this kind of differential equations, we have to use special method to solve it. So in this section, I will talk about solutions to several different types of ordinary differential equations. One is steep equation, the other one is implicit differential equation, where this standard form cannot be obtained easily. So in this case, we have to discuss something about implicit differential equations. And also differential algebraic equations, which is a special form of differential equations. In differential equations, we have a left-hand side as all the x dots. However, for some certain system where some of the x dots will be changed to 0. Some of them are still x dots and some of them are shrink to 0. Then this kind of equation will be referred to as the differential algebraic equation, and we'll talk about that one later through examples. And also the delay differential equation. For instance, the x dot it happens at time t. However, x here may happen at x t minus 5. That means 5 seconds ago. So this kind of equation is called delayed differential equation. So here I will talk about these solutions to this kind of special differential equations. Now let's consider steep differential equation. What is a steep differential equation? There isn't a standard mathematical description to this kind of equation. The first denominator related to this kind of equation is something like this. Suppose there are two curves or two state variables in the equation. One equation changes smoothly, and the other equation may change rapidly. And this kind of equation are usually referred to as steep differential equations. And in numerical terms, this kind of equations are usually very difficult to solve because it is hard to find the step size for this equation. So using ordinary differential equation solver such as ODE equal 5, usually you have to select a very small step at certain point to ensure the solution is correct. And if the step size is selected too small, then the total number of calculation points will be very huge. So this causes memory and not enough memory, such kind of error. No matter what is the memory of your computer, you may have that kind of problem. So for this kind of problem, we cannot use ODE equal 5. We should have to use specialized functions for steep equations. For instance, there is a solver called ODE 15S, where S stands for steep. This is a standard method, and this method is always very accurate. However, for certain differential equations, this one will not work. And this one could be used as the substitute to the equation solver. However, for certain normal ordinary differential equations, this one will not work as good as this one. And here, 1,5 means the order of the solver changes automatically between 1 and 5. The order will change automatically according to the solution itself. It changes automatically. So sometimes it may use first order approximation, that is the Euler method. And sometimes you can use a high order solvers. So the order may change automatically. So sometimes this kind of algorithm may not be very good for standard ordinary differential equations. And it is very effective for steep equations. Now the question is, how can we check or how can we make sure that one equation is steep or not? This is a big question. And this question cannot be solved, cannot be answered because there isn't any method to check whether the equation is steep or not before you solve it. So what you need to do is to try to use ODE 45 first, and for quite a long period of time you do not find any solution, then you terminate the solution process of change. This is the second one. So I think this is only a feasible way to check whether an equation is steep or not. There isn't any existing method to check it before solving it. So now let's go back to the same problem. If μ is 1,000 and the solution period is 3,000, then I said with the use of ODE 45, it may take quite a long time and you cannot get the result. However, with the use of ODE 15S, the result can be obtained immediately. And this is the result. And these are not vertical lines. If you zoom this part, so the mouse is not quite good. If you zoom this part, then you will find the response would be something like this. And the zoom. So the mouse in my computer is not quite good. It should be something like this. It is not vertical lines. It is also dynamic. But changes very rapidly. So it is hard for ODE 45 method to select the proper step size. That is why with the use of ODE 45 we cannot get good results. And there are several examples you can try. In the slide, you can run it on your computer to see what's the difference between the ordinary differential equation solver and this one. What is the difference in speed and solvability. And now let's consider implicit differential equations. So normally the so-called implicit differential equations are those equations that cannot be transformed in this form. So you cannot solve it using ODE 45 solvers. And let's see an example first.